And with this, we're gonna transition to the promised talk about using BPF for lightweight Android profiling, which I guess hopefully will connect some of the dots between the SketchViz question that we had and its usage in Android.
Hi everyone, my name is Riham and I'm a software performance engineer at Facebook. I work with the mobile profilers team and I mainly focus on building profiling tools for Android. Today we're going to be talking about the latest tool that we are using in our Android profiling toolkit, BPF. I will not be getting into a lot of details about BPF. I'll just be giving some general information. But if you're really interested in learning about BPF, I will be sharing a lot of resources at the end that you can go to and learn a lot more about it. Before we talk about BPF, let's talk about tracing in Linux. Linux tracing can be confusing at first, especially if you're new to the space. There are so many tools, and I know that at least for me, when I started to hear about them, it was kind of hard to understand the landscape, to understand how these tools work together. I heard about things like kprobes, uprobes, and trace points, but I also hear about things like BPF and BCC and perf. So what does it mean? Like, how do these things work together? I came across this great graphic by Julia Evans, which actually made things a lot more understandable for me. So you can think of Linux tracing systems as kind of three different types of things that work together. You have data sources, ways to extract the data, and then front ends that kind of interact with the ways to extract the data. Data sources can be the event itself, the thing that you want to look at. So it can be a kprobe or a uprobe, a trace point, a user-defined trace point, various types of events that you want to look at. The other layer is the way to extract this data, and this is where you have things like BPF, perf, ftrace, various tools. The last thing is front ends that actually interact with these tools. So for something like BPF, for example, you have things like BCC or BPF trace or various tools that you can use to interact with BPF. So we'll talk briefly about each one of these parts. We'll start by quickly talking about our data sources. Data sources can be either dynamic or static. They can also run either in kernel space or in user space. So let's talk about dynamic tracing. Dynamic tracing means that you don't need to change your code to enable the tracing. You can just find a function that you think is interesting and immediately start tracing it. This is obviously very powerful, but it also has its drawbacks because if things change, if the function name changes, then you lose your tracing. On the other hand, static tracing is built into the code. You actually put a trace point in your code and you add the information that you care about in it. So this is always guaranteed to be there. It's always going to be fire. Even if the function name changes, then your trace point still exists. For dynamic tracing, in kernel space, you have kprobes. Kprobes will attach to syscalls. You could say, I'm interested in sysopen. There's also the kretprobe, which is similar thing to kprobe, but instead of attaching at the beginning of the function, you can actually attach at the return of the function. This allows you to look at things like return value, latency, different data that you could only get at the end of the function. The equivalent of it in the user space is uprobes. It's very similar. It works in a very similar way. The same thing for uretprobes. So let's say you're interested in learning about memory allocations. Well, you could go and put a dynamic trace point, a uprobe, at the malloc call in libc and say every time this gets called, I want to get some information about it. So in user space, dynamically, you can configure your uprobes, collect the data that you want. In terms of static, you have trace points in the kernel space, and you have USDT, which is the equivalent, but in user space. The second thing we want to talk about is ways to extract data. And BPF is just a way to extract data. BPF stands for Berkeley Packet Filter. The name doesn't mean much because it was originally designed and used for packet filtering, but as time went on, it turns out that the way it was doing this packet filtering could actually be very useful for other things. So the way it works is it allows you to run small, certain user provided code inside of the kernel. This gives you visibility into things that were very hard to have visibility into before. It gives you the ability to answer questions that were extremely hard or even impossible to answer, because the kernel has visibility into things that you would normally not be able to have visibility into. Obviously, running code in the kernel can be very dangerous, and one of the big benefits of BPF is it actually verifies the code before running it. So it guarantees that your code is actually safe to run inside of the kernel. For example, it's very easy for you to say that you want to create a BPF program that tracks every I/O operation on a device. You would be able to just write the code to configure the BPF program to track these and send you back an event when this happens. So safely, very fast compared to other tools, and then it's also a very powerful tool for you to get information. One of the biggest benefits that we saw also from using BPF is how lightweight it is. It's minimally intrusive to your application, and when you're not collecting data, it's basically at no cost for you. So let's talk about an example. One of the things that we wanted to look at Facebook is understanding our native memory allocation, the native memory allocations from our applications. This is very important for understanding not only the resource usage, but also it affects reliability greatly. We need to understand where we are allocating the native memory, where we are releasing it, which memory is not being released, and which stacks are allocating this memory. So first attempt, we tried to collect this data, and we were successful at collecting the data using a combination of various technologies that are either by Facebook, internal technologies, or malloc debug, and various other tools that are available for Android. We were able to get the result we want, but let's look at the performance of the application as we collect this data. Well, as you can see, it has a great impact on performance. We are getting the data that we want, but at a great cost. This is the same data as we get it from BPF. Obviously, the performance impact is very small compared to what we were getting before. So this is what we mean when we say that it's actually very lightweight. The data that we get from BPF is actually exactly the same data that we were getting from the other methods, or even more. We are getting our memory allocations, we are getting the stacks of these allocations, we are getting the timestamps of the allocations, the sizes, but at a much lower cost. Here you can see that we are able to visualize this data in one of our visualization tools and see it as a flame graph or flame chart. BPF comes in two different flavors or two different ways to look at the data. You can choose to get counting or aggregate data, but you can also get sampling. Counting gives you an aggregation of your data. You could say that you are interested in understanding the total memory allocations that occurred, or you're interested in understanding the amount of time that you spent in specific calls, or how many files were opened by your system. So you're more interested in understanding the summary of your data rather than the details of the data itself. And BPF can give you this data in forms of map, and you can think of maps as just data structures. Like you could think of it as just a hash map, or maybe a table that has a list of values. So this is the first way you can look at BPF data, by counting. The other way that you can look at the data is through sampling. And in this case, you're actually interested in the actual details. So you could go and ask BPF to send you information whenever a memory allocation happens. You want to know everything about this memory allocation. You want to know the size of it. You want to know the stack of it. You want to get the timestamp of it. So this is another way to look at the same data. The last thing that I'm going to talk about very briefly is the front ends, and we're going to focus mostly on the front ends that are used to get data from BPF. Well, to write BPF programs are running inside the kernel. They're bytecode programs. So you could write it in bytecode, which can be a little bit challenging, especially if your assembly code is a little bit rusty. Fortunately, there are some much easier to use front ends. There is BPF trace, which is designed to be a very simple command line tool. It's very easy for writing one-liners and actually getting information about things, events that are occurring that you're interested in. So you can see some very simple examples here. You could just say, I want to get information about every sys file open. You could just tell it, every time this gets called, give me the file name that was opened. You could request more information if you want. So you could say, well, I also am interested in knowing the stack and maybe the timestamp of this call. You can configure it through this one-liner to actually get you this data. You can also look at some aggregate data. So you could say, well, I just want to know how many page faults are occurring per process, or you could even look at summary of cache misses for your process by PID. So BPF trace is a very simple to use. It has a very, it's very easy to just ramp up and learn how to use BPF trace, but it's not very powerful. It's not going to get you everything that you need. So there is another tool that's called BCC. And BCC actually allows you to write BPF programs, but in different language. So you could use, there is a Python interface, for example, which is very simple, very straightforward, and you could just configure it to track the same call, like you could track the sys open calls, but also get more information about it. So now that we kind of got an idea about BPF and how we can interact with it, we can talk about how we are using BPF for Android. BPF has been available on Linux for a few years now, but it only recently started being available on BPF. And we realized that we can use it for many different performance tools or investigations, but the biggest tool that we found it useful for is tracking consumption metrics and investigating superbugs. Consumption metrics are what we define as critical but also limited resources that can affect your application. These can be things like file opens, disk operations, memory allocations, page faults, anything that's not necessarily the latency of your application, but things that will affect the performance, the latency, or the reliability of your application. The other thing that we're using it for is tracking bugs. It can track a lot of bugs, but it's been extremely useful for tracking a specific class of bugs that we call superbugs. Superbugs are bugs that have been around for like a long time. They have probably been looked at by a large number of developers. They might involve several releases, and we have not been able to successfully understand these bugs or root cause them. So the first thing that we talked about was tracking consumption metrics. How are we using BPF to track consumption metrics? We talked about different data sources. We talked about key probes and U probes and hardware and software events. And we also talked about collecting the data in two different formats. We can have an aggregate format or a sampling format. For consumption metrics, what we have is we have an aggregate map. So what we have is your application is running and it's keeping track of the consumption metrics that it thinks are interesting. For example, we're keeping track of how many page faults we have in the app now, how much memory was allocated, the number of disk operations that are happening, the files that were opened, the files that were closed, and all of this data is being written to an aggregate map. Let's say that your application started and it can fire a start event. When this event is fired, we can actually go and capture a snapshot of our aggregate data. So we can look at the specific time where the start event occurred, how much memory we had allocated, and how many page faults we had, and how many files we had opened. You can then go and perform your test scenario, and then at the very end, you can fire an end event event and kind of do the same thing. So take a new snapshot of your aggregate map. You can look at the same consumption metrics that you were interested in at the point of the end event. By comparing these two values, you can actually see which metrics have regressed. So you could go and find that you are now doing 50% more memory allocations than you were doing before. Once you get this data, it's very important to have a way to correlate this data with specific events. So you can go and look at the point of time at which you had this big increase in memory. If you're capturing your data at certain intervals, or you're capturing your data based on certain events, then you can kind of create correlation between the increase in consumption and the user activity. We talked about collecting data in sampling mode. Well, let's say you found that you have a regression in memory consumption. In that case, you can actually go and request for another run with the same scenario but with more details. So now that you know that you have regressed memory allocations, you can go and actually request data to see where exactly these memory allocations happened, which function calls and which stacks. And you can possibly compare the two stacks and see which ones are creating the more allocations. You can find calls that were added or things that were rearranged that are actually causing these additional allocations. This helps for regression detection, but also for understanding application performance in general. The other thing that we talked about is using BPF for tracking superbugs. And it doesn't have to be superbugs. BPF has been very useful for tracking a very big class of bugs. But in this case, we can talk about an example where we had something that was very hard to understand without BPF. So we knew that we had something that was leaving file descriptors open, but it was very hard to know what exactly is leaving these files open. So we created very small BPF programs. This is using BCC, and you're simply attaching to the sysopen event and the close event. So you can see when a file was opened, you can get the stack for the open, and then you can see when a file is closed. And what the application is doing is it's getting the file open calls, it's creating a map and putting in it, this is the file descriptor that was opened, and this is the stack that opened it. Every time it gets a close event, it goes and finds the matching open event and says, okay, this file is now closed. At the end of your application, you can go and see which files were opened but were not closed, and what are the stacks that actually open these files. So in this case, we actually found that we had one of our audio files was being left open, and we were able to kind of get the exact stack that was opening it and leaving it open. So just by doing this very simple matching between the open event and the close event, we were actually able to get a lot of information about the resource leak. The other use for BPF is just understanding memory leaks in general. And we talked about BCC. BCC actually has some built-in tools, and one of them is a tool that detects memory leaks. So for this one, we actually didn't need to do anything specific or anything extra to understand the memory leaks that we have. The application simply attaches to the malloc, calloc, realloc, all memory allocation events, and then it also attaches to the free event. It keeps track of memory addresses, and it keeps track of which ones of these were left open versus which ones were closed. If a memory address is allocated, then you have the stack that created this allocation, and at the end you can create kind of an aggregate data that says, like you see here, this stack created that many allocations, and total they're using this much memory. So this way you can kind of find out which stacks or which operations are leaking your resources most and address those. The last scenario, and the one I think is actually the most interesting scenario, is memory corruption. If you've ever had to look at memory corruption issues, then you know that these are notoriously hard to troubleshoot, because when you know about a memory corruption, it's usually too late to deal with it. It's usually something that's happened in the past, and you're just dealing with the side effect of it. So historically, we've been able to look at memory corruption issues using address sanitizers, but these are not free. You need a specific build. You need it's just not something that you could run when you hit an issue. You need to be very well prepared to specifically capture capture memory corruptions. Well, BPF actually allows us to look at this. So this is one real-world scenario where we had a memory corruption issue, and we kind of knew that we have like something related to mmap and munmap. So we thought we would try BPF and see if it would actually be able to capture this corruption, and it was almost immediately captured it. So what's happening is there's a call that's doing mmap and there's a call that's doing munmap, but it's doing it for a mismatch size. It's doing unmap for more memory than the memory you actually had mapped. Well, we just needed to attach a U probe to the mmap call and the ret probe to the mmap return call to get the address. And then we just needed to attach another probe to the munmap. And in a way, very similar to the one we used for the file descriptor leak. Like in this case, you're just keeping track of each memory address and the state of this memory address. You're also keeping track of the stack that created the mmap call and the stack that did the munmap call. And at the end, you just go and compare if something is trying to do unmap, but the mmap did not happen with exactly the same size. If this is bigger, then something might be off. We should warn on that and then look at it later. So in that case, you could see that it almost immediately captured the case where we are doing unmap with a size that's just a little bit bigger than the matching mmap. BPF has been around for a while on Linux, so there are so many tools that have already been built around it. The vast majority of the cases, you will actually find a tool that does exactly what you want. This is a list of the BCC tools that you can use, and this list is just growing every day. So what's the future? How we are planning to use BPF? Well, we saw some screenshots of being able to use BPF for regression detection. This work is still in progress, and we're really hoping that what you're going to get is you'll just have automatic runs that go in the background and that tells you about every resource that you have regressed and the stack that you regressed it from. The other thing that we are looking at is Sapiens, and this is kind of randomization engine, or more like a chaos monkey. So ideally we want to have BPF running in the background. So if you do something that causes a memory corruption, even if there is no crash that happens immediately when you do that, then you at least kind of get something that tells you, well, you know, something happened here and this might not be the right thing. You might have freed memory that has already been freed, or you might have done something that caused memory corruption. Then ideally you would be able to get some information about what you did. The last thing is we are hoping that maybe someday we would be able to have developers using devices that have BPF running in the background, so that we can dynamically configure it to detect any of the user bugs, any of the super bugs that we have been struggling to reproduce, such that if this randomly happens on maybe a developer device or a dogfooding device, then we want BPF to let us know right away. Well, thank you so much for listening, and please let me know if you have any questions.
Awesome. Thank you so much, Riham. It was an amazing talk and an amazing showcase of the power of BPF and how we can leverage it for mobile development.
Thank you.
Let's see if we have any questions. Like so far, we don't have any. So I'll just, I guess, go ahead and ask them. I'm, I guess, first of all, curious about your thoughts on whether we can leverage BPF for something like the SketchViz technology that Lee presented earlier today. Like, do you think it's possible to have something like that on mobile?
I think it is. So at least from my understanding, the SketchViz was kind of pretty independent from where exactly the data is coming from, or maybe that was my understanding. I could be wrong about that, but it seems like it will accept the data from any data source. So I don't see why it wouldn't accept just the BPF data. It shouldn't really matter if it's collected from Android or like Linux or anything. It should. I think it can accept this data just as raw information and just display it. And I can see that Lee has just commented saying you have actually written a BPF script that generates the needed data. So yeah, it seems like this is definitely possible.
Awesome. And what do you think about using BPF for something like black box? Do you think it's possible to use it in prod, at least at some point. Obviously, right now it requires some special kernel support, but do you see it being used in production in future?
So that part is a little bit challenging because, as you said, it requires kernel support. I think also there would be some concerns about like security because it's still there is a verifier and there is definitely some like things that protect, but I don't see that happening like very soon just because of these concerns, security and also like as I said, just the availability in general. How do you like it requires specific configuration of the kernel when you're building it. So I don't see that being available very soon. Having said that, like at least on developer devices, maybe we can just install a custom version of Android that has these built in so that people can opt in and get give us this information from their devices.
So Adam has a question. Do you use it locally rather than to get data from the field?
Yes, that is true. So right now we're using it locally, either on like your own device, on emulators, or in the lab environment.
Awesome. Thank you, Riham.